Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture 40, which is devoted to plasma nitriding. This is part of module 8 in this NPTEL course on environmental degradation of materials and surface engineering. So we have already discussed last time that when we introduce nitrogen to the surfaces of not only steel but any other any element which actually has an affinity for nitrogen, be it iron or titanium or chromium or aluminium or molybdenum, any element which has nitride forming ability, and when exposed to high temperature containing nascent nitrogen or atomic nitrogen, is likely to form initially solid solution. Since the solubility of nitrogen usually is very low in all these elements, after about a few percent, and not even 1%, but less than few fractions of a percent, say 0.2, 0.3 atomic percent of nitrogen dissolution, the surface starts developing nitrides. And most of these nitrides are interstitial compounds, usually line compounds, so they are very hard and extremely high hardness with complex crystal structures. They also are very brittle. And in the process, we actually accrue a lot of benefits in terms of wear resistance, hardness, chemical inertness or corrosion resistance, and even at times residual compressive stress on the surface. So like we are seeing here, say for example, this helical gear component, so we have here the gear teeth, and these gear teeth in the pristine condition are able to maintain perfect geometry, exactly the perfect geometry like this. But after a certain amount of service, exposure to the service condition, we see fair amount of damage of the surface. So the tooth which was initially like this, let's say like this, after the wear develops degradation in this region, which we don't want. So this is the profile that needs to be maintained, and not this kind of a profile which is formed due to surface degradation or wear or progressive loss of material. So in order to ensure that no such damage occurs, we would like to create certain layer on the surface, compound layer on the surface, which will give this protection. We have seen how this can be done by either gas nitriding or liquid bath nitriding. Of course, liquid bath nitriding has its own dangers which needs to be kept in mind, but gas nitriding is a fairly efficient and well-practiced operation through which one can improve the wear resistance of steel, iron bearing, or titanium, aluminium, or other alloys. So in this lecture, we are going to discuss the other possibility of nitriding, which is by using plasma. And we'll realize that plasma nitriding scores several advantages over gas nitriding or liquid bath nitriding. So first of all, as the name suggests, plasma essentially is a quasi-neutral combination of state with combinations of not only the neutrals, the atomic states, but electrons as well as ions. So ions, electrons, and neutrals together is the state of plasma, which is a metastable state and can be created either by very high thermal activation or electrical discharge or some other mechanisms. So plasma or ion nitriding or any of these forms of nitriding is a method of surface hardening, and the creation of plasma is through a glow discharge mechanism, which creates this nascent or elemental form of nitrogen ready for diffusion and reaction. So first we have to create a low pressure region, lower than the atmospheric pressure. So that means we go through evacuation process. At low pressure, we apply electrical discharge or cause very high temperature for the species or the gas species to get ionized and excited, usually by application of an electric potential difference, and then we create this plasma. The high voltage electrical energy is used, and that not only creates the plasma but also causes nitrogen ions to accelerate and impinge on the workpiece. We have to remember that the workpiece essentially is the cathode, and the surface of the container acts as the anode. So we need a vacuum pumping system, vacuum chamber, sample handling stage, because in many cases we might like to rotate the sample during the operation, and a power supply unit, of course. As I said, the sample itself is connected to the stage, which is cathode, and the surface of the wall is the anode. So we have to introduce the right kind of a gas which will get excited and ionized through the glow discharge process and allow nitrogen to be available in the form of nitrogen ion ready for incorporation onto the surface. So this is the overall system. So we have quite a few components, starting from the electronic component, temperature controller and indicator, thermocouple to measure the temperature, pumping system to evacuate. This is the overall chamber. This is the stage which can be rotated or kept fixed. This is on which you load the sample, and the sample, of course, is the cathode, and the surface is the anode, so that positively charged cations can be accelerated towards the sample. So we have a process window or monitoring window, transparent, through which we can monitor the process. We have pumping system, valves, electrical insulation, power supply, and of course switch for continuous or pulsing kind of applications. So the process typically is very well described by a so-called glow discharge mechanism. So this glow discharge, the glow essentially, typical violet kind of a glow comes from the plasma that is created, nitrogen plasma that is created. So we introduce essentially nitrogen and hydrogen. Unlike ammonia in case of gas nitriding, plasma nitriding is based on combination of nitrogen and hydrogen. In fact, in the proportion of something like about 95 to 5, even 98 to 2, the bulk of the thing is only hydrogen, and just about 1 or 2% of nitrogen. So presence of hydrogen is very important, because that actually not only helps in creation of the plasma but also is very important for etching the surface and making the nitrogen ions to penetrate. So subsurface modification occurs because of surface adsorption and subsequent diffusion of nitrogen. So we create the nitrogen ions, and that gets adsorbed and then diffuses inside as a nitrogen atom. So we create high hardness and wear resistance. That's exactly why we are interested in plasma nitriding. The process actually improves not only hardness and wear, but also can improve the fatigue strength and corrosion resistance of the components. The most important part is that we can ensure the dimensional stability. There's not much of a large scale overheating and contraction due to cooling. There's practically no thermal shock because temperature rise and decrease is controlled, and the process is very environment friendly. There's no toxic or objectionable gases like ammonia. So we are dealing with benign nitrogen-hydrogen mixture. So this is the chamber, and when the plasma is created, then this is the kind of a glow that we see, and which surrounds the sample, and that's how we actually can create nitriding. So the thermocouple measures the temperature and maintains exact temperature isothermal state. And as I said, this is the anode and the sample itself is the cathode. So the process actually involves quite a few very important stages, and each one of them has its own specific significance. The first one, once we create the initial plasma, at the time of formation of the plasma, there is quite a bit of sputtering exercise possible. So essentially the ion gets accelerated towards the surface at some high velocity, and they actually we have a lot of the plasma also. This could be nitrogen hydrogen mixture. It could be also initially argon filled chambers, so that the argon ions can be accelerated for sputtering some of the atoms from the surface, and that in turn can create certain defects. So the first stage is the sputtering stage, which also removes oxide layer to a large extent and cleans up the surface and makes further nitriding or subsequent nitriding more efficient and possible. So sputtering followed by plasma reaction. The plasma reacts with the surface, and the species gets, for example, when the plasma is created, then the plasma reacts, and the plasma reacts and forms certain compounds. Then there is surface diffusion possible, and after surface diffusion, the surface adsorbed atoms could diffuse further in, and that is through thermally activated diffusional process. We also see radiative heating process, because once we create the plasma, there is a lot of radiation happening inside the chamber. Also, defects are created right in the very first stage, and these defects further improve in the diffusion coefficient, and there is always some amount of collision happening with the ions and the surface, and due to this ion surface collision, ion solid collision, there could be further increase in temperature. So one needs to maintain proper isothermal state by proper control of applied electrical potential difference, gas pressure, external heating, and so on and so forth. So the important process parameters are the current density, the applied electrical power, and the potential difference, the vacuum or the pressure level inside the chamber, and of course the right gas mixture. So just randomly chosen components, starting from bearings to base plates or drill bits or machine tools, shafts, gears, all these are subject to various kinds of plasma nitriding process. And the process, this is what we have discussed already. This is no different. Initially, when nitrogen get dissolved in iron, so we form solid solutions. And the solid solutions actually could be in the BCC state itself. And if you dissolve quite a large amount, then you can even convert that into austenite, and that austenite can get stabilized. So apart from such solid solutions, then the various forms of nitrides may form, Fe4N or Fe3N or Fe2N. So, so initially just the dissolved phase, extended austenite, then epsilon nitride, even zeta nitride, and so on and so forth. So if I have a simple nitrided layer, if I subject a component, let's say iron or steel, to plasma nitriding, with two different possibilities, one with a fairly coarse grain structure, say of the order of 15 micrometer average grain size, and in another case, I do the same treatment with the same parameters, identical condition, with an order of magnitude smaller crystallite or grain size. So if you have large grain and if you have small grain for the same volume and same composition, then one thing is for sure, that apart from the diameter being smaller, the boundary area, the grain boundary area that we have is certainly going to be much larger per unit volume for the small grain structure. So we all know that diffusion can occur through the bulk. Diffusion can occur also through the surface. So it can be bulk diffusion, or it can be surface diffusion, it can be grain boundary diffusion. So in all these cases, the surface diffusion is the fastest form of diffusion. So diffusion through surface is faster than diffusion through boundary, than diffusion through volume or bulk. So if you create a small grain structure, what you expect is that in the process, the nitrided layer that you form will be thicker, will be fairly thicker than the nitride layer one could form with coarse grain structure. And this is exactly what is seen here. What we also see is that if there is, since a nitride layer is actually very thin, normally nitride layer gives you chemical inertness or corrosion resistance. But if that layer is removed because of very firm salt spray, then there could be a possibility that instead of maintaining the same corrosion level or oxide formation level, the oxide formation level can significantly increase, as we are seeing in this particular case, which was a nitrided steel, but because of certain reason during the salt spray process, if the layer is damaged or broken, then the amount of oxidation can significantly increase. But in general, what is of interest to all the industry level application is the fact that the plasma nitrided layer is always thicker and deeper than the gas nitrided layer. So any day plasma nitriding will be more efficient and desirable than gas nitriding process. So if I compare, then say all the three processes, gas nitriding, liquid bath nitriding, or plasma nitriding, what are we seeing? So gas nitriding is a very precise, it requires very precise temperature control, and hence we can maintain predictable case depth and hardness and dimensional stability. So the entire surface can be covered by various forms of nitrides, and it's basically a batch process, though one can go for a continuous process, but then maintaining the proper gas mixture and pressure and so on may be difficult. So these are the, both batch and continuous, both are possible, but it can be made batch processes for limited number of components. So these are the advantages. But on the other hand, you require a very good surface cleaning, because otherwise if you have an oxide layer, then nitrogen cannot penetrate, and hence there will be no nitride or white layer formation. You need masking if you don't want nitriding to happen. For example, in certain areas which you want to leave it open for some other subsequent treatment, then you need to mask something so that those areas of the surface so that nitrides don't form there. And because of nitriding, there could be certain increase in surface roughness level, and that happens because the nitrides actually create certain corrugation on the surface, because dimensionally their lattice parameters are bigger than the matrix alpha iron lattice parameters. If you go to liquid bath nitriding, you have higher hardness and wear resistance. The core hardness, the core remains the same, so you're not affecting the core. The corrosion resistance improves, which is true for any other nitriding process also. And because of slightly lower temperature and a liquid bath, so that the temperature actually is maintained very uniformly and distributed, so there is less risk of distortion. So these are all good points. The disadvantage or the demerits are the following, that first and foremost, you're talking about a huge environmental and safety risk. You're dealing with cyanide and such fumes or very high level of corrosion of the tank and so on, and you cannot shut down, you have to run it 24/7. So these are all disadvantages. And you also need quite a bit of washing or cleaning of the components to, if the salt still sticks to the surface, then it's going to continue to corrode the surface. So you have to take care of that and follow up with some washing. In case of plasma nitriding, much of these are not needed. First of all, the advantages. Excellent process control and can be done for stainless steel or titanium or any other metallic component which are prone to formation of nitrides. You actually can do quite a bit of sputtering at the beginning of before the nitriding process starts, so that the surface is cleaned, and you also create certain defects which subsequently may help. And you don't use any hazardous gas at all. You use only hydrogen-nitrogen mixture, unlike in case of gas nitriding where you use ammonia. So instead of ammonia, here you're using only nitrogen-hydrogen mixture. And before that, you could also have certain sputtering done by argon. The disadvantage, of course, is that you form a compound zone, but that is true for any nitriding process. Temperature control is not so easy because there are a synergistic process. As you create the plasma actually sputters, then there is concomitant ion bombardment, which itself can generate temperature locally, so temperature may rise. So temperature control becomes a little more difficult if it is particularly done for a longer period of time. You do create certain surface roughness, but that's bound to happen for any nitriding process. And the process is little more complex because you push your components, then seal, then evacuate, then backfill, then create the plasma discharge by applying electrical potential difference and so on. In fact, in some special case of plasma nitriding, one actually can do even ion implantation by applying negatively charged potential or negatively biased potential and pulsing it at very high frequency. So the nitrogen ions get bombarded, or they tend to bombard the component from all sides if you apply high negatively biased potential to accelerate the ions and impinge onto the surface. But that's what we have not discussed here right now. So essentially, if one compares all these, then one sees that in case of gas nitriding, we need certain surface activation for processing stainless steel. The compound zone actually can be, in order to create a good compound zone formation, we have to do surface cleaning and grinding or machining to remove the oxide layer at the beginning. In case of liquid bath nitriding, maintenance is a nightmare because you're dealing with extremely toxic and corrosive substance. The bath, you have to maintain the bath, you can't switch it off. So there is an energy cost and so on and so forth. But in case of plasma nitriding, some amount of masking may be required, but other than that, we are using basically nitrogen, hydrogen, argon, or methane, and so on. So these are all very non-harmful gases, and you have better nitride layer formation and a higher thickness layer formation. So if we now take all the nitriding processes into our consideration, and not just plasma nitriding, gas nitriding, or liquid bath nitriding, this is more efficient because plasma actually does help in cleaning the surface before the nitriding process starts. So the initial feed wise, in plasma nitriding, we are using nitrogen-hydrogen mixture, maybe argon in the beginning, whereas in case of gas nitriding, we are using ammonia primarily as a feedstock. Plasma is the quasi-neutral state that you all know, comprising the ions, neutrals, and electrons. We need high vacuum because otherwise creating plasma is very difficult, because you need electrical discharge, and that can happen if you have higher pressure. Then the energy that you input gets scattered and easily diffused, whereas in case of low vacuum, the energy density is higher for creation of plasma, or ejecting electrons from the neutrals is more possible in case of high vacuum. So the phases that form in plasma nitriding or gas nitriding, they are nearly about the same, but the thicknesses differ, and even composition also differ to some extent. As I said, that the top layer at the very surface, if this is the component, and if let's say this is the white layer formed, then the very thin surface on the very thin layer on the surface will have the highest nitrogen containing compounds, more of them at the top surface than at the bottom. So this could have the Fe2N sort of very high nitrogen containing compounds, and as you go down below, gradually the not only the concentration of such nitrides decrease, even nitrogen concentration itself decreases. So somewhere in between you end up getting a diffuse layer which will contain nitrogen dissolved ferrite or solid solution, and below that will be the substrate. So white layer, then interdiffusion region, and then base substrate. So this is the white layer, and it's called white because I already told you that it doesn't etch at all if it's so chemically inert. We create residual stress on the surface because of the tendency to expand, tendency of expansion of these nitrides as they form on the surface. And this actually is beneficial because the state of stress is compressive in nature, acting towards each other, and that actually can improve the fatigue strength and also wear resistance. High hardness not necessarily means high wear resistance. This is something we have to understand. So the layer that we form, the so-called white layer, is also very high hardness but also fairly brittle. So if the load application is very fast and intermittent, or if the load is of impact type, then there could be certain chipping off of the hard nitride phases from the surface. So nitriding is very helpful, but we have to understand that in some specific cases of application where the surface there is a lot of vibration, lot of intermittent impact or something there, it may actually lead to certain chipping off of the phases from the surface. You should find out what are the components which actually are routinely subjected to gas or plasma nitriding and to what extent. Plasma nitriding is not only confined to steel. I told you a number of times that it actually is applicable to all nitride forming elements. And we generally select only those which actually have a tendency for such nitride formation. I think that's all. We'll stop here. So we have covered quite a lot in terms of surface engineering based on change of composition, initially with carbon, and now we discussed with nitrogen. And now onwards we'll move into the other forms of surface engineering. Thank you very much.